Well, how did they renormalize it? What is renormalization? Renormalization is a way to cut the number. In physics, there's two kinds of infinities. One infinity is an infinitely small number. When you find an equation that gives an infinitely small number, you can discard it. Because it's a very small, thing, so you can, not pay attention to it. However, there's another kind of infinity called nasty infinity in physics. And nasty infinities is when you solve an equation and it gives you an infinitely large number. When you get an infinitely large number, then you can't just say, I'm going to ignore this. And so that's why it's called nasty. Although current physics has been ignoring what I'm going to show you for almost 100 years. Because it was almost 100 years ago that they found that the density of the vacuum is infinitely dense. So when they do that, when they find infinity like that, what they try to do is find a constant to cut the number so they get a finite number. So in this case, they use the Planck's distance. 1.616 multiplied by 10 to the minus 33 centimeters. It's a very, very small number. It's the smallest thing current physics think the universe can do. Meaning that 10 to the minus 33 centimeters, which is a point with, 32 zeros and 1, right? Is very, 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 very small. And it's calculated using the Planck's constant, using gravitational fields and electromagnetic fields, and it says that it's the smallest oscillation, the smallest vibration the universe does, the smallest teeny weeny thing. And you can think of it as a photon going through itself. How long of a wavelength that would be, how many centimeters that would be. So they took this and they said, hey, that might be my mom. And she's like, you're talking again? Do you ever stop talking? So what they did is they took a centimeter cube of space and they said, how many of these little vibrations can we stick in there? That will give us a finite number of oscillation in a centimeter cube of space. We'll have a finite number for the density of the vacuum. So they put all those little oscillations in there and calculated how much they would weigh. What's their mass? Each one has a mass of 10 to the minus 5 grams. So now you can get a density. And the answer is 10 to the 93 grams per centimeter cube. 10 to the 93 grams per centimeter cube. That is a very large number. That's 10 with 92 zeros. Okay? You all notice in your bank account, when you add a zero, it's really good. Right? If you have like 4 zeros and you add one, it's like, oh, that's good. And then you add another one, it's like, oh, yeah. Then you add another one, it's like, oh, now we're talking. Right? So it goes up pretty quick. Like imagine you got like some 50 zeros and you keep adding. Imagine 93 zeros. Oh. Let me give you an example. If you took a centimeter cube of space and took all of the stars in the universe, every single atom we see out there, and you squish them all into a centimeter cube of space with this huge trash compactor, you know. Imagine how dense that would be. All the universe in a centimeter cube of space, like, huh. What would be that density? The density would be 10 to the 55th grams per centimeter cube. You would still be 39 orders of magnitude off, less than the density of the vacuum, with the whole universe in a centimeter cube of space. So the vacuum density that you're made of, that all of your atoms are made of inside your body right now, is a lot of vacuum. It has this incredible, infinite amount of energy, or extremely large at least. And, you know, you may have access to that. People tell me all the time, I have a hard time visualizing infinities. That's because people try to visualize infinitely big. And that is not very possible because you have limited senses outside yourself. You can only see a few miles out. You can only touch a few feet away from you. But internally, there is a possibility that you could have access to infinity, towards the infinitely small. This may be why some of the greatest masters that have walked the earth have been trying to tell people, turn your senses inward. Go towards the center. Go towards the vacuum. Go towards stillness. Because there you will connect with the foundation of creation. You will connect with, they might have called it God, the Bindu point, the infinite potential, and so on. You know, to take a few minutes every day to do this might be a good practice. Just to find that power, just to find that center at the center of your existence. So you might say, well, you know, these equations are crazy. You might say, I don't believe the vacuum is that dense. Maybe physicists are doing something wrong. Well, somebody like that thought like that in 1947 and said, hey, we need to be able to measure if this vacuum density is really there. Does it really exist? His name was Casimir. And in 1947, he calculated, how can I measure the vacuum density? And he came up with this idea. He came up with this idea that if you put two plates very close together, very, very close together, you will eliminate the long wavelengths between the plates, but not on the outside of the plates. So you should get a difference between the energy on the outside of the plates and the energy between the plates. They should get pushed together. I have a small animation you can see. Hello? There we go. You can see, let me play it again. You can see that there's little waves between the plates and there's a lot of waves on the outside of the plates. So as you bring the plates together, some of the wavelengths get eliminated between the plates, so you get an external pressure pushing the plates together. Well, when he did the calculation, you realize that in order for the plates to get close enough to eliminate enough frequency so that the vacuum could push the plate together, the plates would have to be microns apart, which is a very, very, very teeny distance. 1947, nobody could polish plate micron precision. There was no way to get two plates that close together. So it took until 1990 before we could get plates that close together. And when we did, when we brought the plates together, sure enough, they started to get pushed with exactly the force that was predicted by Casimir in 1947. This is a laboratory proof that that energy is really, really, really there. It's everywhere, and it's inside you. And since it's inside you, since it's the energy that makes you, you have access to it. And remember, those frequencies, these energy represent information. That means you have access to an extremely large amount of information. This starts to be able to explain many paraphysical phenomena that we see. You know, remote viewing. Obviously, if the vacuum connects all things and it's everywhere, if you go inside yourself, you can get the information of what's going on very far away from you. It starts to explain entanglement. Why particles interact. Like, for instance, new experiments were done when you can scrape a little bit of cells off the tongue of a person, put them in a petri dish, and keep them alive, and monitor their energy level and all this. And then you send the person away, and you put all sorts of devices on them to monitor, you know, the change in temperature, changes in brain frequency, and so on. And as they're going through their day, for instance, in this particular example, this lady during the day had an appointment at the doctor to get a mold removed. And everything was stable, both in the cells and in the data that was on the person, until she got to the doctor, started to get nervous, and she saw the knife that the doctor was going to cut the mole off with. When this happened, her vital signs, everything in her data, jacked up. And you can see on the graph, everything go up. And exactly at the same time, in cells that were 15 miles away from that person, the cells' data started to jack up at the exact same time. You can see the graph are exactly the same. So this starts to be understood because the vacuum connects all these things together. So with the help of Dr. Rauscher, Dr. Rauscher is a physicist that has been collaborating with me for now 6 years. We started to write a scaling law. And the reason why we wrote a scaling law, because when I was talking to Dr. Rauscher, she was saying, if this is true, if the vacuum is full and the vacuum is dividing to create our reality, then when we graph the objects in the universe on a graph, they should all start to line up. They should show organization. They should show that things are self-organized. And so we did this graph. This is the radius of the object. This is its energy level in hertz, frequency. And we started with the universe, the size of the universe and its energy level. Now, it is an interesting thing there. If you take the size of our universe and you put in the amount of mass we see in the universe obeys the Schwarzschild condition. The universe obeys the condition of a black hole. Did you know we live inside a black hole? I mean, when you look up at night, it's black. We know there's enough stars that it should be completely white. But when you look at our universe and you were to point a laser at it, the light of the laser would get curved by the gravitational field of our sun a little bit. And it would curve that light a little bit. And as it curves it, then the light would continue to go, and then it would hit another star, and it would get curved by the gravitational field of that other star. And then another one, and another one, and another one, and another one, and it would come back. Because there's too much mass in our universe obeys the condition of a black hole. Was that expected in my theory? Absolutely. Because if you can divide to infinity everything, then all you have is different scales black holes. All you have is divisions of the space, division of the vacuum. And in each division, you have infinite amount of mass. If you can divide the atom into smaller particles and smaller particles and smaller particles, and each particle has mass, then you can add all the mass, you will get a black hole. So we live inside a black hole, so that would mean that all the things we see inside there, we are on the outside of those black holes. So what do we see there? We see the radiative side. We see the white hole part of a black hole. We call it a star. We call it a galaxy. We call it a quasar. Now I want to make clear, this is not the standard model. Just in case you were confused about that. Because this theory says there's a black hole at the center of our sun. It says there's a black hole at the center of our Earth. It says there's a black hole at the center of atoms. Well, when we start to plot all these other objects, so this is quasars, galactic centers, stellar objects, they all started to line up as predicted by my theory. We plotted even atoms and subatomic particles. This is the Planck's distance, 10 to the minus 33 centimeters. I'm getting a cramp in my toe from too much surfing. And so this linear progression functioned perfectly, even including atoms, which are usually not included in the, in the cosmological sense. Meaning, here I'm crossing from Einstein's equation to quantum theory. They all seem to line up. So obviously, the two are related. Interestingly, if you take the microtubules, which is the little entities, they're the little structures that make up the surface of your cells. They're little tubes, they look like little wormholes. You take their energy level and their radius, they intersect the scale very, very close to its center. So even your biology is part of this scale. You are part of this incredible scale from extremely large, the universe, all the way to billions of times smaller than an atom. You're right there on that scale. You're part of that system. You're transferring information from the outside to the inside, from infinitely big to infinitely small. You're embedded into the structure of the vacuum. It's communicating with you, and you're communicating with it. You're part of that feedback. You're like an extension of space looking back at itself and learning about itself. That gives you a different sense of your responsibility. That gives you a different sense of your relationship to the universe. You're no longer just an insignificant little dot in the universe. All of a sudden, every single dot is crucial to the learning structure of our universe. We know that the electrons and positrons that makes up your atoms are appearing and disappearing into the vacuum. This is why there's uncertainty about where they are and where they're going. This is how the vacuum is informed. You're appearing, disappearing, appearing, disappearing, really, really fast at the speed of light. And when you disappear, you're the vacuum. You're informing the vacuum. And then when you reappear, you're experiencing the material world. And when you take your experience, you feed it back to the vacuum. And like that, the vacuum is feeding you back your experience. You are creating that reality. You all following me? Now, you will hear that in the New Age and in the spiritual groups. You create your reality. You'll hear it very especially if you're having a fight with your partner. You created this. It's very convenient in this matter. Well, that is only half of the equation. Because if there's a feedback, if you're informing the vacuum and then the vacuum is giving you back your experience, then reality is creating you as well. So you're creating your reality and then reality is creating you. Because you see, if you only have half of the equation, if you say you create your reality, which is becoming popular, even in the physics community, if everybody created their own reality, it would get very lonely. We would never meet. Everybody would be in their own reality. Going, where'd everybody go? Right? But we have a consensus reality. Because there's a medium that connects us all, that's making sure that there's organization between all interpretation of reality. So that when you think something, when you interpret reality, then you feed it to the vacuum, then it's modified by everybody else's experience, so that when it comes back to you, it's coordinated with everybody else. You guys follow this? Very important part. You can't forget that part. Otherwise, you could say, hey, I'm too hot today. Let's turn the sun down. And then the poor guy in Alaska is like, oh, it's cold. And so, there's coordination. So the concept, you all heard about the butterfly effect? The concept that a butterfly in Africa can bat its wings and produce a hurricane in Florida is not complete. It's not complete. The probabilities of that happening is very, 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 very low. Right? Because if every time a butterfly flapped his wings, there would be a hurricane in Florida, you would have Floridians in Africa with guns, you know, going, stop doing that. You're upsetting a lot of people over there. No, it would take thousands, millions of butterflies batting their wings together to even produce a probability that a hurricane could be created from it. Otherwise, it's almost not possible. Huh? Because the whole morphogenic field has to have enough power to make a change. This is why I'm talking to you today. Because in order to make this change I talked about at the beginning of the conference, we must come together. We must gather our forces. We must all come to a different understanding together so that it becomes something in the morphogenic field that has power, so that it can make that change, so that the butterflies start to make a hurricane. And that is because we are all connected in this feedback loop of creation, in this feedback loop of learning. So never, ever, ever forget the second part of the equation. Reality is influencing you. The world is influencing you. As well, that will help you, because some people, spiritual people, said, you know what? I went to all the seminars, even Nassim Haramein, and I read all the books, and I did all the meditations, and I still can't manifest this blue Camaro that I want. What is wrong with me? Well, in order for you to manifest something significant, you have to overcome all of the other manifestations that are occurring from all the other reality. It has to coordinate. So when you're sending information into the vacuum, when you're sending information into the space, then when it comes back to you, it's always a little bit modified. It's not exactly as you would expect it, because if it was, you would stop learning. You would have manifested the ultimate reality for you a long time ago, and you'd be sitting there going, man, this is boring. I'm not learning anything. What is going on, right? The universe would end. But because the whole system is modifying everything all the time, when you feed it to the universe, it comes back to you a little change. And so you keep learning, which means the universe keeps learning. Okay. Well, you know, if you look at this graph, well, this graph is refusing to work. Let's see. You find that this, you find that these two data points can be black holes. These actually can be black holes too. But you know, the atom in standard physics would not be a black hole. If you tell a standard physicist, oh, I saw this guy that says that atoms are black holes, he will say, not possible. So this is why I dodge a lot of tomatoes, you know. Because my reality has not quite caught up with the rest of the scientific community reality. Is the atom really a black hole? Is that possible? Well, I thought about it for years. I was looking for a way to understand how that's possible. Currently, standard physics would say no. It's not massive enough. It doesn't have enough energy. But then I realized, wait a minute. Remember this number, 10 to the 93 grams per centimeter cube? It has been completely ignored by the scientific community for a very long time. Actually, the standard answer to this number is it has no physical meaning. What? You mean the largest, most intense energy ever found has no physical meaning? How is it pushing two plates together if it has no physical meaning? So I started to say, wait, maybe they ignored this. And sure, they did. They didn't consider the amount of energy inside the nuclei of an atom in the vacuum fluctuation. They just left that out. So I said, let's see how much energy is inside the nuclei of an atom in terms of vacuum density. How much vibration of the vacuum is inside a proton, the nuclei of the atom. You all following this? This is where we're going to do a little math. You all ready? Not bad math, easy math. Okay, so I then took the radius of a proton and I said, how much volume is inside the radius of a proton? So this is 4/3 multiplied by pi multiplied by the radius square cube will give you the volume of a proton, a spherical volume. You all following this? And so the volume of a proton is approximately 10 to the minus 39 centimeters cube. So it's extremely small. It's teeny, teeny, weeny little volume, right? Very, very, very small. Like 39 zeros, you know, and a 9, right? Very, very, very teeny volume. And then I said, okay, so now if I take that volume, if I divide it by the density of the vacuum, I will know how much vacuum density is inside the volume of a proton. So you see, it's in grams, centimeter cube. The centimeter cube cancel out, it leaves grams. And that's 10 to the 55 grams of energy in the vacuum inside the proton is still present. Did you all follow this? That means that the vacuum density, there's still 10 to the 55th grams of vacuum oscillation inside the proton, of information. Why was I not surprised for this number to come out? Because what is that mass? The mass of the universe. Why was I not surprised? Remember my statement? The vacuum connects all things. So that means that all the little oscillation of all of the protons in the universe experiencing the universe from their own perspective would have to be in each proton for the vacuum to know what everything is doing. So when that number came out, it right away mathematically proved that we are all one. That was significant for me because, you know, making a statement without an understanding of how that's true is not complete. But when you start to understand the mathematics on how that's true, now you've got something really powerful going. So in the paper I published, and that's why I was saying that paper was so radical, I thought I was going to get kicked out of the conference, not receive an award. Right? Is because in that paper, when I make this equation, I put a very simple statement. This may be evidence that all protons are entangled. All protons are connected through the structure of the vacuum. And that's how the system can self-organize. Because the vacuum knows where everything is. So this, you know, is a very large number. Do I need all this energy for the proton to be a black hole? No, because even this in the size of the universe is enough to make the universe a black hole. So I don't need anywhere close to that for the proton to be a black hole. So then I calculated what actually amount of the energy of 10 to the 55th gram is needed for the proton to become a black hole. Don't panic. This is called the Schwarzschild radius, or the Schwarzschild solution. Carl Schwarzschild was the first man to find a solution to Einstein's equation. When Einstein published general relativity, he didn't solve it. He just published the concept. The concept that gravity is not a force inside an object, but that gravity is the result of an object distorting or curving space-time. And when he published it, he thought, well, you know, the equations are complex and all this. It's going to take a long time before we find a solution. But Carl Schwarzschild was back from the front. He was at war in Russia. And while he was sick, he actually solved Einstein's field equation. And it's called the Schwarzschild solution. He died 2 weeks later. But he sent the solution to Einstein just on time. And Einstein was quite surprised. He said, oh, wow, there's already a solution. But when you solve the solution, he said, oh, it produces a black hole. It produces a singularity. He didn't call it a black hole because that was coined later by John Wheeler. But it produced a point of infinite density. And he didn't like that part. He thought, well, you know, maybe my equation breaks down there. We'll just take the weak curvature, not the high curvature. So this equation is used all the time to calculate gravitational fields in the universe, but they ignore the fact that it needs a black hole, it needs a singularity at the center for the curvature to actually occur. So it tells you what radius a black hole would be. Friends, this is R sub s, is the Schwarzschild radius, equals 2 multiplied by the gravitational constant multiplied by the mass divided by the speed of light square. So this, if you know the mass, the gravitational constant, you can solve this to figure out what would be the radius of a black hole. Like where does a system would reach the condition of a black hole. But in this case, I know the radius. What I'm trying to figure out is what mass I need out of 10 to the 55th for the proton to be a black hole. So this is the equation just like this. Here's the radius. This is the gravitational constant, so 2 multiplied by the gravitational constant. The mass, I don't know what it should be, and this is the speed of light squared. So I got to change the equation around so it equals mass. You all following this? So now I take the speed of light squared, I bring it on top. The radius is over here, and I bring the gravitational constant on the bottom, and that will give me the mass. And the answer is 10 to the 14 grams proton. And now I can calculate how much of 10 to the 55th gram that's inside the proton did I use to make it a black hole. The percentage is 10 to the minus 39%. A very, very, very teeny weeny little teeny beady little amount of the vacuum becomes coherent to produce all of the atoms in our universe. Very teeny weeny amount to produce all of the material world. So what I'm saying in that paper is that maybe just a teeny weeny amount is necessary of coherency, not randomness. Coherency occurs in the vacuum to produce the material world. Well, you know, this is remarkable. Again, you know, that number keeps coming out. Did you all notice? 10 to the minus 39, or 10 to the plus 39, 10 to the plus 40. This has to do with Dirac, which was a famous physicist. It's called the large number hypothesis. Dirac noticed that this large number keeps coming out everywhere. And he made a hypothesis that there's a relationship between the atomic level and the universal size that relates this large number. So, you know, this is all nice. It's pretty, it's simple. But if you ask a physicist, a quantum physicist especially, it will tell you that it is wrong. Why? Because 10 to the 14 gram proton is actually in the standard model, they say it's 10 to the minus 24 grams is the mass of a proton. So you will say, oh my God, you're off by 10 to the 38 grams. See, again, that number. Very close, you know, 10 to the 38, 10 to the 39. This is what happens to me when that happens. Has he gone insane? I'm 10 to the 39, 10 to the 38 orders of magnitude off. Oh! What am I going to do? You got to remember, I'm looking at the mass inside the vacuum of the proton. So, luckily, since I've been meditating for a long time, the Buddha comes in and says, stay calm, it's okay. The key is the strong force, dear one. What is the strong force? Well, almost 100 years ago, we discovered that protons have charge, right? That's why we call them proton. They're positively charged. And that charge would repel them from each other. If you take two magnets of the same polarity and you push them together, they will repel, right? So when they found this, they said, you know, the repelling power of, it's called the Coulomb force, is very, very strong. How can the atoms stay together? Atoms should have never formed. And so to solve this problem, they said, oh, well, gravity is not strong enough because at the time, they didn't have black holes. Right? So they said, we're going to invent a new force. We'll call it the strong force. Because it has to be very strong. In fact, it would have to be the strongest force in the universe. And they assume that it was there because the atom is together, so there must be a force squishing it together. But they give no physical understanding, no physical meaning, no source for that energy. They put the strongest energy in the universe in our equation without saying where it came from. You know? And then they said the force is mediated by gluons. The glue. Okay. One way to do physics. I call it physics as you go. You got a problem here. You just put in the strongest force in the universe. Don't worry about it. You calculate the mass of the universe. You're missing 96% the mass of the universe. Oh, you just invent dark matter. You put it in there. Oh, look, the equation works now. Don't worry about it. Right? So they invented the strong force, and they said, they calculated how strong it would have to be, and they made it exactly the strength it has to be to compress the protons together. And then a big problem occurred. Later on, they discovered that there was quarks, little smaller particles inside the proton, in a teeny, teeny radius that are charged, and they said, oh, now these things are compressed into a smaller radius again. We need a stronger force than the strong force. But they couldn't really call it the strong force. I mean, that just doesn't look good. So they came up with another scheme. The color force. It's nice, it's artistic, you have colors. And they said, oh, the color force will make the color force infinitely strong. Like that, if we find anything smaller, now we have infinitely strong force to deal with it. But think about it. If you have an infinitely strong force compressing into a small volume, squishing, confining into an infinitely small or a very small volume, what does that make you think of? A black hole. That's right. How do you say black hole in Spanish? Awareness? I'm not going to even try. I'm going to have to tap into the vacuum of Spanish language. And so, this squishing was not given any source. Imagine throwing in your physics an infinitely strong force, but not saying where it came from. So obviously, when you ask a physicist how strong is a strong force, they don't really have math that tells you how to calculate it. They have latex QCD, but there's no comprehensive answer. So they tell you a comparison to something they know, which is gravity. So they say, how strong is a strong force? They say, well, if gravity is 1, guess what? The strong force is 10 to the 38 to 10 to the 39 times stronger. You see, the difference between the standard model and my model is that in my case, I accounted for the energy necessary to confine, to hold everything together. They just threw it in with no source. So in my case, it's gravity that's doing the job. That's holding everything together. Gravity in standard model is the weakest force of the universe. In this model, gravity is the strongest force of the universe. It holds everything together. It is the vacuum curving, it's the vacuum spinning towards singularity. That is at the center of existence, the force that holds to the center, the mother that holds the child. And so, you know, I knew that this would not convince a physicist. So what I did is I wrote a scaling law. And in the scaling law, actually in the paper, the scaling law has more data points. And the paper that's on the net is not complete. It's a draft paper. I'm not putting the complete paper on the net because it hasn't been published yet, so I'm waiting for it to be published in the journals, but then I'll put it on the net. But we put data points. Here's the universe. And so this is the log of the mass against the log of the radius, right? Mass and radius. And I said, okay, forget equations. If I'm wrong, my proton is going to be completely off, and the standard proton is going to be correct. So, you know, from the Planck's mass, which is teeny, 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 to the universal size, I put galaxies, I put quasars, I put the sun, even the Earth, pulsars, and then I put the Schwarzschild proton. Look at that. Perfectly on the line, right? Perfectly on the means of all these data points. And then the standard proton, completely off. Off in left field. This doesn't lie. This is fundamental. You can't just, you know, you can't debate this. This is just data. This is not some idea. This is not some mathematics. This is data. And so here, you can see that this is a problem. Why is it a problem? Well, a physicist will say, but why then, when we do experiment, we measure the mass as 10 to the minus 24 grams? Well, because when we measure the mass of a proton, we measure it after we knock it out of an atom. right? Or we measure it far away from the surface event horizon of the black hole, where the gravitational field is weak. So what we're measuring is a frame of reference from our scale to the frame of reference of the proton, far away from it. So what I'm saying is that if you were measuring near the event horizon, you would find that it obeys the Schwarzschild condition, because that's where the vacuum is actually producing the proton. This is where the vacuum is interacting, producing the proton. You all following this? So it actually works. I think we're going to take a break now to get you a chance to use the washrooms and maybe get a tea or a bite. Thank you so much for this morning session. Thanks for your attention. Thank you. Thank you. We're going to have some fun this afternoon.
Pensacola, where's Pensacola?